Exercise 2 or question 2 of exercises 4.6 on page 196 of your lecture notes. This is EGM 90 Advanced Aerodynamics. Simply asks you to determine the flow pattern in a nozzle with exit area, with a throat area, of 0.7 times the exit area, and a static pressure at exit px 0.7 times p0. Now we know that there are three, for a condyne nozzle, there are three options, and we've got to decide which one of those options is the case here. Well, I guess there are four, the fourth option being that the flow never makes it to supersonic at the throat, so it remains purely subsonic all the way through. And what we will consider here is, first of all, is whether or not the flow manages to achieve a supersonic condition at the throat, Mach 1, and then whether or not it continues to accelerate supersonically through the diverging section, or returns to subsonic conditions and is purely subsonic through the diverging section. And then the fourth option we have is whether or not there's a shock present in the diverging section of the nozzle. So the starting point for these problems, as we're getting used to now, is to try and work out what the non-dimensionalized mass flow is at the exit from the duct, assuming that there are no shock waves. And it's worth stating that assumption. Assuming no shock waves present, we can say that m dot root cpt naught over a, sorry, that should be a, we're trying to work this out at the exit, is equal to this non-dimensionalized mass flow condition at the throat, a star p naught, and of course this is only true because if there are no shocks, p naught upstream is equal to p naught at the throat, which is equal to p naught at the exit. If there are shock waves present, p naught is not constant. The stagnation pressure will drop through the shock wave. And we just spot that the only thing that's changing here is the area, so we can just simply take out this ratio a star over ax, which is something that we know. We also know, either because we've memorized it or because we look it up in the compressible flow tables, that m dot square root of cpt naught over a star p naught at the throat, if the nozzle is choked, i.e. the Mach number is 1 at the throat, is 1.281, and the question tells us that a star over ax is equal to 0.7. And that number turns out to be, if you type it into a calculator, 0.897. So let's just remind ourselves what our options are. Let's sketch a little diagram. Showing Mach number against distance along the nozzle. Upstream in the chamber the flow is at rest at 0 and it accelerates up to Mach 1 at this point, so this is the throat here. And then there are two options for the flow, assuming there are no shock waves present beyond this point. It can continue accelerating supersonically through the diverging section. We'll call that option 1. Or it can return to subsonic conditions and decelerate to a subsonic exit value, and we'll call that option 2. Now, to find out the behavior of the flow under case 1 or option 1, we simply scroll down through our compressible flow tables until we find m dot root cpt naught over a p naught equal to 0.897. And what we find is that option 1 corresponds to mx equals 1.79, and if we scroll horizontally across the compressible flow tables, we will find that P over P naught in that case is equal to 0.177. If we scroll back up through the compressible flow tables, we will find that there's another value, a Mach number value, that gives you a non-dimensional mass flow of 0.897, and that Mach number is 0.46. If we scroll horizontally across the compressible flow table, you'll find that at Mach number 0.46, P over P naught is equal to 0.865. Now, the condition that we have in the question is that P over P naught is actually equal to 0.7, which means that we haven't got option 2, the purely subsonic case where the flow accelerates to Mach 1 and then returns to subsonic, because that would require a P over P naught of 0.865. But similarly, the pressure difference across this duct is not significant enough. It's not, the P over P naught value isn't low enough, because it would need to be 0.177 in this case to have purely supersonic flow in the duct. So the option that we must have is that somewhere in the diverging section there is a shock wave. Now, in the lecture today we did look at how you would then go on to work out where that shock wave sits, which I'm not going to do in this case, but we know that this is the actual condition. So if you had to describe the flow through this nozzle under these conditions, you could say that the flow accelerates to Mach 1 at the throat. It continues accelerating supersonically. At some point in the diverging section there is a shock wave present which reduces the Mach number, it reduces the total pressure, and then the flow exit the nozzle, presumably subsonically, although we don't actually know that in this case, we haven't gone that far. If you were in the lecture today, you would have seen how to go on and determine exactly where and how strong that shock wave is in the diverging section, but that was all you needed to do for question 2 of those exercises.